Hello, I'm going to be going over the bounds exam questions. Now, I still don't have a printer, so I've had to hand write these out. So let's just get into it. First question. So here we've got I is equal to V over R, where V is 250 to the nearest 5 and R is 3,900 to the nearest 100. Now, as soon as you see that you've got numbers and they've given you a degree of accuracy, you know you're working with bounds, you know you're going to get some marks if you're writing down some error intervals. So even if they're not saying error intervals here, I know what I want to do is write down, well, V, if it's to the nearest 5, half of that is 2.5, so this is between 247.5 and 252.5. And here, 3,900 to the nearest 100, that's going to be between 3,850 and 3,950. So I'm going to get marks straight away for writing these down. Now calculate the lower bound of I to 3 decimal places. So here, the lower bound, well, I'm doing a division. So to make this the smallest value it can be, I'm going to do the smallest value of V divided by the greatest value of R. So here it's going to be 247.5 divided by 3,950, and in my calculator that is going to be 0.06 3 to 3 decimal places. Next, question 2, a bit more of a real life example. So I've got 60 golf balls, each weigh 42 grams to the nearest gram. Well, that means it's between 41.5 and 42.5. What is the greatest possible weight in kilograms of the 60 golf balls? I've kind of shortened the question there. So here I'm doing a multiplication, greatest possible, so that's the upper bound, so I'm going to be using the biggest value it possibly can be. So that is going to be 60 times by 42.5. So 60 times by 42.5 is 2,550. Let's remember this is in grams. It wants my answer in kilograms, so that divided by 1,000 is 25. Oh, I divided by 100, didn't I? That is 2.55 kilograms. Question 3. Here, bit of interleaving. We've got a right angled triangle and I've got 2 lengths, so I know I'm using Pythagoras' theorem. Here, A is 8.3 centimeters to the nearest millimeter, and B is 6.1 centimeters to the nearest millimeter. So, again, let's just straight away, that's going to be 8.25 and 8.35, and this is going to be 6.05 and 6.15. Calculate the upper bound for C. So we know that C is going to be equal to the square root of A squared take away B squared. Now the important calculation within this is the takeaway. Now if I want an upper bound for this, I want this takeaway to give me the biggest possible value it can, and as if I have the biggest possible value of A, take away the smallest possible value for B. So my upper bound for C is going to be the square root of 8.35 squared take away 6.05 squared. And that is going to be 5.754997.828. Oh, had some bleeding. Question 4. Let's change to red to make it a bit clearer. Question 4. So here, d is equal to u squared divided by 2a. where u is 26.2 to 3 significant figures and a is 4.3 to 2 significant figures. Now, as we saw in the error interval video, if I have significant figures, I've got to think, well, actually in this question, what has it been rounded to? So here, really it's been rounded to 1 decimal place. And again, here it's also really been rounded down to 1 decimal place. So here, I'm going to have 26.15 to 26.25. And here I'm going to have 4.25. And 4.35. What is the upper bound of d to 6 significant figures? So here, d is a division. So again, I'm going to want to have, for the upper bound, the biggest this can possibly be is if I have the biggest possible value of u divided by the smallest possible value with a. So my upper bound of d is going to be 26.25 squared divided by 2 times 4.25. So again, in the calculator, that gives me 81.066, and 2. So that is 6 significant figures. Part B, the lower bound of d is 78.6003 to 6 significant figures. By considering bounds, write down the value of d to a suitable degree of accuracy. So here we want to see what is the most accurate I can be between these two numbers. So the actual value of d is somewhere between here. What is actually the most accurate I can say? Well, they're not going to agree to 1 decimal place. They're not going to agree to the nearest integer. Here, the most accurate I can be is actually not very accurate, so I would say d is equal to 80. Both of these would round to 80 to the nearest 10. You could also technically say to the nearest significant figure, 1 significant figure. With these questions, I haven't actually written it down here, but it also says give a reason. So the reason for this is as both the upper and lower bound agree, round to, it's probably better, round to this. So let's have a question where it just straightforward asks, by considering bounds, calculate m to a suitable degree of accuracy. So I have my calculation, I have my values that have been rounded. Here, s is to 2 decimal places, so that means we've got 3.465 and 3.475 for s, and 8.1315, that is an awkward number, and 8.1325 for t. By considering bounds, here I've got to work out, as we had here, both the upper and lower bound for m. So let's do the lower bound first. So my lower bound for m, I'm going to try and make this the smallest it possibly can be. So for that, I want to do the smallest possible value that s can be, divided by the biggest possible value that t can be. So that is going to be the square root of 3.465 divided by 8.1325. So 3.465 square rooted divided by 8.1325. And so that is 0.2288903839. For these kind of questions, you're going to want to write down everything that appears on your calculator, because you don't know how accurate you need it right now. For the upper bound, I want this to be the biggest it possibly can be. It's the opposite of this. I'm going to have to use the biggest possible value of s, square rooted, divided by the smallest possible value of t. So that is the square root of 3.475 divided by 8.1315. And that is equal to 0.229248623. So, what do both of these agree to? So, here, we start changing on the third decimal place. Now this would be 0.229, and this would also be 0.229 if we rounded it. They wouldn't agree to 4 decimal places because this would be 2292 and this would be 2289. So the most accurate I can do it is that m is equal to 0.229 to 3 decimal places. You could also say 3 significant figures. And again, as both upper and lower bound round to this. So, rest of these questions are that kind of question where we're considering bounds to give a suitable degree of accuracy. And I'm going to be mildly lazy and not write down that full sentence anymore, but when you're giving reasons, that's what you need to say. So, here, by considering bounds, as always, let's give the error intervals for this. So we've got 10.75 and 10.85. We've got 75.055 and 75.065. This time, be careful, it's big square roots. I'm going to press the square root button first. So my lower bound for this is all square rooted. So the smallest value this can be is the smallest value of s divided by the biggest value of t. And that is 0. I should probably write down the calculation. 10.75 divided by 75.065. And then the upper bound is going to be the biggest value of s divided by the smallest value of t. That's going to be 0.3802113301. So, where do these both agree to? So, here, we change on the second decimal place. This would round to 0.38. This would also round to 0.38. So p is equal to 0.38 to 2 decimal places. Again, because upper and lower bound both agree to this. Now, let's take this skill and apply it in some different contexts. So here, train travels 487 kilometers in 3 hours. Well, that's the nearest kilometer, and that's the nearest minute. Well, let's be a bit more specific then. That is 180 minutes. By considering bounds, work out the average speed in kilometers per minute. Great unit to be using there because I don't have to worry about anything awkward. It's just 180 minutes. So here, I need to have my upper and lower bound for this. So that is between 180.5 179.5, and this is going to be between 486.5 and 487.5. So, kilometers per minute. I'm doing a division again, so I want to have for my lower bound the smallest possible value for kilometers divided by the biggest possible value for minutes. So that's going to be 486.5 divided by 180.5. And my upper bound is going to be the biggest possible value for kilometers, 487.5 divided by the smallest possible value for minutes, 279.5. So we've got 2.695290859. And 2.715877437. So here it changes at the first decimal place, and well, this would round to 2.7, this would also round to 2.7, so that is 2.7 kilometers per minute, again as both upper and lower bound agree to one decimal place. Now, last question, density. Now, we're not great fans of density at the moment. Please remember that density is equal to mass divided by volume. Now, for this question, we've got a cuboid with measurements to the nearest millimetre. I've got 13.2, 16.0, 21.7. So that really is 13.15 and 13.25, 15.95 and 16.05, 21.65 and 21.75. The mass is 1,970 grams, correct to the nearest 5 grams. So half of 5 grams is 2.5, so that's going to be 1967.5 and 1972.5. Now, by considering rounds, work out the density of the wood to a suitable degree of accuracy. So my density here is going to be mass divided by volume. I'm doing a division, so that means I want the biggest possible mass. Sorry, for the lower bound, I want the smallest possible mass divided by the biggest possible volume. So, smallest possible mass is 1967.5 divided by the biggest possible value. It's using the upper values for all of this. Volume is these all multiplied by each other, so that's 13.25 times 16.05 times 21.75. And that is going to equal 0.42536774546 centimeters per gram. And upper bound then is going to be the biggest possible mass, so 1972.5 divided by the smallest possible volume, so that's going to be 13.15 times 15.95 times 21.65. That is 0.434382850. So again, where do these agree to? So they change in the second decimal place. This would be 0.43. This would also round to 0.43. So this is 0.43 grams per centimeter cubed to 2 decimal place, as both the upper bound and lower bound agree to this value. Thank you.